Picture this. You're chilling in the passenger seat of an autonomous car, just cruising down the highway. Suddenly, a completely random, novel object, maybe some bizarre piece of debris, blows right into the middle of the road. The car's AI? It's never seen this thing before. Ideally, the system should instantly realize it's uncertain, flag the issue, and hand control right back to you. But what if, instead, it confidently misidentifies that debris as a harmless shadow and steers straight into a concrete barrier? Or think about a medical AI that confidently misdiagnoses a rare disease simply because it doesn't know what it doesn't know. Welcome to our explainer for today, where we're going to dive deep into this incredibly dangerous phenomenon of AI overconfidence and uncover a revolutionary mathematical framework that is finally solving it.
Here's our roadmap for the breakdown today. We'll start with the AI confidence problem and the uncertainty dilemma, dig into the probability trap, and then introduce possibility theory. From there, we'll see exactly how the DAPPr framework works to actually deliver smarter, safer deep learning.
All right, let's jump straight into part 1, the AI confidence problem. This is our core mystery.
So, we have these highly trained, deeply sophisticated neural networks processing absolutely massive amounts of data, and yet they routinely make catastrophic errors with total 100% confidence when they encounter things they haven't seen before. Why is that? Well, this quote right here hits the nail on the head. The key to AI safety isn't just about making models smarter or stuffing them with more training data. The real frontier here is self-awareness. We absolutely have to give these models the ability to quantify their own predictive uncertainty. Look, if an AI doesn't know the answer, it literally needs to be able to say, hey, I don't know.
To actually fix this, we first have to agree on what uncertainty even means to a machine, and it really comes in two distinct flavors. First up, you have aleatoric uncertainty. Think of this as the intrinsic noise baked right into the data itself, like a super blurry pixelated photo. It's irreducible, you just can't fix it. But the second type? That's epistemic uncertainty. This is the AI's actual lack of knowledge. It's a fundamental blind spot, but the good news is, it's reducible if the AI just learns more. This right here is our main target today. We need the AI to realize when it's operating inside one of those blind spots.
Which brings us to section 2, the uncertainty dilemma, or what has historically been a massive dead end.
You might be wondering, if we know we need to fix epistemic uncertainty, why haven't we done it yet? Well, data scientists have basically been stuck choosing between two seriously flawed options. On one hand, you've got Bayesian methods. Now, these are mathematically beautiful, super rigorous, but for modern deep learning, they're practically computationally intractable, meaning they are just way too slow. On the other hand, you have second-order predictive modeling. This is lightning fast, but it's mathematically unprincipled. It relies on quick heuristics instead of solid math. It's kind of like being forced to choose between a car that's perfectly safe but only drives 1 mile per hour, or a blazing fast sports car that doesn't have any brakes.
To put that rigorous Bayesian approach into perspective, the problem is the astronomical computational cost. To calculate that epistemic uncertainty we want, traditional Bayesian learning requires the system to integrate over the entire massive parameter space of a deep neural network. For the giant networks we use today, that cost is just unthinkable. It's a massive bottleneck that usually requires running huge, clunky ensembles of models, and that simply cannot scale to real-world, split-second applications.
So let's look at section 3, the probability trap. This is where things get really interesting. Here is the crazy plot twist. Both of those previous methods we just talked about, they are caught in a fundamental structural trap, and that trap is probability theory itself. You see, probability theory forces you to slice up a single pie of 100% certainty. So imagine an AI is completely clueless about an image it's looking at. If it guesses there's a 10% chance it's a dog, the math artificially forces it to subtract that 10% from the chance that it's a cat. But the AI doesn't know anything. Assigning probability to one random guess absolutely shouldn't take away from another guess when the system is in a state of total ignorance. It's a total logical fallacy.
Enter our hero in section 4, possibility theory.
If probability is totally the wrong tool for the job, what's the right one? Well, it's a decades-old mathematical concept that is finally getting its moment in the spotlight. Possibility theory. Let's finish that analogy from earlier. If probability theory is a single pie that you have to perfectly slice up into 100%, possibility theory is more like a room with a ceiling. Multiple objects can reach all the way up and touch that ceiling without taking a single inch of space away from each other. Instead of probabilities that have to sum to 1, possibility theory uses plausibility, with a maximum limit of 1. So if the AI is completely ignorant, every single potential classification can be rated as highly plausible at the exact same time.
This perfectly models epistemic uncertainty because it fundamentally acknowledges when knowledge is incomplete.
Moving right along to Section 5, let's talk about how DAPPr works, which is the elegant bridge making all of this happen. Okay, so how do we actually take this conceptual room and ceiling analogy and turn it into working code? Researchers have unveiled a brilliant framework called DAPPr. That stands for Dirichlet-approximated possibilistic posterior predictions. DAPPr works in 3 logical steps. First, it defines a possibilistic posterior over the parameters, basically evaluating how plausible the model itself is given the data. Second, it projects that plausibility directly into the prediction space using those ceiling-like supremum operators we mentioned. And finally, because doing that perfectly is still mathematically tricky, it creates a highly accurate approximation using learned Dirichlet possibility functions. By doing this, it completely bypasses that brutally expensive Bayesian integration we looked at earlier.
It's a pretty ingenious shortcut. Instead of wandering through the vast, high-dimensional parameter space to try and calculate the integration the old-school way, DAPPr takes parameter plausibility and projects it straight down into the prediction space. It swaps out that heavy, slow integration for a really smart, constrained optimization.
Now, I know, terms like possibilistic projected posterior probably sound a bit intimidating, but the actual DAPPr pipeline is remarkably simple in practice. To implement all this complex theory, you literally just take your standard network logits, the raw predictions, and you apply a very simple soft ++1 mathematical transformation to them. That's the whole shebang. It instantly turns those raw numbers into valid possibility functions.
And the end result? It is lightning fast. We're talking about a methodology that can be written in roughly 10 lines of code. It just drops seamlessly into your existing deep learning workflows, essentially acting as a drop-in replacement for the standard cross-entropy loss function you're probably already using. So, you get the rigorous mathematical safety checks of Bayesian math, but moving at the blazing speed of modern tech.
Finally, Section 6, Smarter, Safer Deep Learning. Let's check out the results.
Let's look at the hard evidence from the benchmark tests in the paper. Think about it. As you feed an AI more and more training data, its uncertainty should logically go down, right? When we look at previous standards like evidential deep learning, or EDL, as the data increases, it actually starts glitching out. Its uncertainty occasionally spikes up. But when you look at DAPPr's performance, it behaves exactly like a logical system should. It smoothly drops its uncertainty as it learns more, all while maintaining consistently higher accuracy across the board.
Furthermore, a truly safe AI needs to instantly know the difference between data it understands and data that is completely alien to it. Notice how DAPPr brilliantly and cleanly separates familiar, in-distribution data from alien, out-of-distribution data. The older EDL models overlap those two things heavily, which means they are routinely confusing weird alien data with familiar data, and that is exactly what leads to those overly confident, catastrophic errors we talked about at the very beginning.
And when you put it through the ringer across rigorous benchmark tests using heavy-duty datasets like CFAR and Tiny ImageNet, DAPPr consistently takes the crown. It beats out state-of-the-art second-order methods in overall accuracy, in confidence estimation, and in successfully detecting that alien out-of-distribution data.
So let's wrap this up. Why is DAPPr the definitive solution to our mystery? Well, it relies on a rock-solid foundation built on possibility theory rather than forced probability. It offers a mathematically tractable, closed-form solution. It naturally suppresses that spurious evidence that might confidently point an AI to the wrong answer. It does all of this with incredible computational efficiency. And honestly, the best part? It requires absolutely zero architectural modifications to your existing neural networks.
Which leaves us with this final thought. We are currently deploying AI into medical theaters, into autonomous vehicles, into complex security grids. These are environments where machines' overconfidence can quite literally mean life or death. By shifting from the rigid confines of probability to this highly nuanced, self-aware realm of possibility, we aren't just making AI mathematically sound. We are fundamentally redefining AI safety from the ground up. And it really forces us to ask, how will this brand new possibilistic understanding of truth reshape our trust in the machines that are actively building our future? Thank you for joining us for this explainer. Keep questioning and keep learning.